Welcome to Paper Trail, where we make academic research accessible and engaging. Let's see what the evidence says.
For decades, planetary scientists have been baffled by something truly odd about Uranus and Neptune. Their magnetic fields are not just a little off-kilter, they're wildly tilted and severely off-center, defying all standard models.
It's a mystery that's persisted since Voyager 2's flybys in the 1980s. Imagine Earth's magnetic field, which is generated deep in its core and pretty much aligned with its spin axis. Now imagine a planet where the magnetic North Pole is closer to the equator, and the entire field generator seems to have shifted dramatically off-center. That's the anomaly discussed.
And the prevailing theories about the interior structure of these ice giants couldn't quite explain how such a stable yet wonky magnetic field could be maintained.
Precisely. Until now, that is. New research suggests the answer lies in a bizarre, previously theorized but unconfirmed state of matter deep within their mantles, a carbon hydride, where hydrogen atoms don't just flow, they spiral along fixed pathways.
So these planets aren't just wonky. Their very insides might be home to a completely new form of matter that dictates their strange magnetism.
That's what the paper proposes. It's a solid-liquid hybrid where carbon forms a rigid structure, but hydrogen flows through it in incredibly specific helical channels. This quasi-one-dimensional superionic state could be the missing piece of the puzzle.
To understand the significance of this discovery, it helps to rewind to the 1980s. Before Voyager 2, the assumption was that Uranus and Neptune, like Earth, Jupiter, or Saturn, would have magnetic fields resembling giant bar magnets, more or less centered and aligned with their rotational axes.
That was the expectation. Planetary scientists anticipated a neat dipole field driven by a dynamo deep within the planet. But when Voyager 2 swept past Uranus in 1986, its magnetometer recorded something entirely different. The planet's magnetic axis was tilted a staggering 59 degrees relative to its rotational axis.
59 degrees! To put that in perspective, Earth's magnetic axis is tilted by about 11 degrees.
Exactly. And it wasn't just the tilt. The magnetic field didn't even originate from the planet's physical center. The dipole's center was offset by 33% of Uranus's radius, shifted markedly towards the south rotational pole. This offset creates a highly irregular magnetosphere, making the magnetic field vastly stronger in one hemisphere than the other.
So a lopsided, skewed field, far from the neat, centrally aligned picture.
And then, 3.5 years later, Voyager 2 arrived at Neptune. What it found was a similarly chaotic setup. Neptune's magnetic field is tilted by 47 degrees from its rotational axis, and its center is offset by an even more astonishing 55% of the planet's radius. That's about 13,500 kilometers.
That's more than half the planet's radius. This wasn't just an anomaly. It was a fundamental challenge to the understanding of planetary dynamos. The question immediately arose, why are these fields so wonky, and how can they maintain such stability?
On Earth, the magnetic field is generated by convection in a liquid iron outer core, which is deep and strongly coupled to the planet's overall rotation. This coupling helps keep Earth's magnetic field relatively aligned with the spin axis. But Uranus and Neptune are different. Gravitational data from Voyager 2 suggests they have a low-density hydrogen-helium outer envelope, a rocky core, but crucially, a massive intermediate layer, a mantle composed of what are often called hot ices, meaning water, methane, and ammonia.
So a completely different internal structure.
Indeed. The magnetic fields of these ice giants are believed to be generated not in a deep metallic core, but in this shallow, fluid-like mantle, at radii as large as 0.9 times the planet's total radius. Because the field generation happens so close to the surface, the local convective dynamo motions are essentially decoupled from the planet's global rotational motion. This decoupling explains why the magnetic axes can wander and stabilize in off-center, highly tilted orientations.
This explanation accounts for the tilt and offset, but it still doesn't explain the stability and isotropy, the highly directional nature of these fields. A churning soup of water, methane, and ammonia shouldn't naturally produce such persistent, irregular patterns.
And that's where the concept of superionic matter enters the picture, setting the stage for the significant development in the new paper. It suggests that the chemistry and dynamics of that soup are far more structured than previously imagined.
So, before discussing the new research, it's essential to define what superionic matter actually is, because it sounds like something from a science fiction novel.
It's often described as a surrealist limbo, a state of matter that is simultaneously solid and liquid. In a superionic material, extreme pressure forces one set of atoms into a rigid crystalline lattice. That's the solid part. But then, intense heat causes another set of atoms to break their molecular bonds and flow freely through the microscopic empty spaces within that lattice. That's the liquid part.
So, you have a solid framework, but with liquid components moving through it. That's quite counterintuitive.
It is. A significant development illustrating this came in 2019 with the experimental confirmation of superionic water, sometimes called ice X18. For decades, scientists hypothesized that water inside ice giants existed in this state, but proving it was another challenge.
How was something like that created on Earth?
Physicists Federica Capari and Marius Malott from Lawrence Livermore National Laboratory used the Omega Laser Facility at the University of Rochester. Their methodology was quite remarkable. They placed a microscopic droplet of liquid water between two diamond anvils. Then they fired 6 giant, high-powered ultraviolet laser beams at the setup.
Lasers to create planetary conditions?
Precisely. Those lasers explosively vaporized the diamond surface, sending a massive shock wave through the water sample. This compressed the water to pressures of 100 to 400 gigapascals, that's 1 to 4 million times Earth's atmospheric pressure, and heated it to temperatures between 3,000 and 5,000 degrees Fahrenheit.
Conditions similar to what's inside a planet.
Yes, but only for a few billionths of a second. Before the sample could obliterate itself, they fired 16 additional laser beams at a tiny strip of iron foil nearby. This generated a flash of X-rays that passed through the water, capturing its atomic structure via X-ray diffraction.
And what did that brief, violent experiment reveal?
It proved the existence of ice X18. The X-ray diffraction showed that the oxygen atoms in the water had arranged themselves into a rigid, face-centered cubic lattice. Meanwhile, the hydrogen protons spilled free, moving like a liquid through that oxygen framework. Because these freely flowing protons carry an electrical charge, ice X18 is highly conductive. It's also completely black because it absorbs light differently than normal ice.
So superionic matter exists and it conducts electricity via proton flow. That's a big piece of the puzzle for planetary dynamos. But the issue was this hydrogen was flowing in 3 dimensions.
Exactly. While this explained some conductivity inside Uranus and Neptune, it didn't fully account for the highly constrained directional nature required to generate their bizarrely skewed magnetic fields. Furthermore, the mantles of these planets aren't just water. They contain vast quantities of methane, which is CH4. This leaves open the question, what happens to the carbon and hydrogen from that methane under even more extreme planetary conditions?
Which brings to the new paper by Kung Liu and Ronald Cohen from Carnegie Science. This work directly addresses that question.
Their paper, published in Nature Communications, investigates carbon hydride, a compound derived from the breakdown of methane under the crushing conditions found deep within ice giants.
And they push the boundaries far beyond what was achieved with superionic water.
Significantly further. While the 2019 ICE-18 experiment maxed out around 400 gigapascals, Liu and Cohen investigated conditions ranging from 500 to 3,000 gigapascals. That's roughly 5 million to 30 million times Earth's atmospheric pressure. They paired this with temperatures from 4,000 to 6,000 Kelvin, which is about 6,700 to 10,300 degrees Fahrenheit. These are the precise conditions expected at the deepest regions of the ice giant mantles, approaching the rocky core.
So they're looking at what happens at the very edge of the core. And what they found sounds truly unique.
The paper's most striking and counterintuitive finding is the specific geometry of this new superionic state. Under these extreme conditions, the carbon and hydrogen don't form a three-dimensional free-flowing soup. Instead, they form a highly structured quasi-one-dimensional superionic phase.
Quasi-one-dimensional. That's a crucial distinction from the three-dimensional flow of hydrogen in ice-18.
It is. The carbon atoms lock together to form a rigid, ordered hexagonal framework. The researchers describe this visually as outer spiral chains of carbon. But here's the twist. The hydrogen atoms break their bonds and become mobile, but their movement is strictly dictated by that carbon lattice.
They're not just flowing anywhere.
No, the hydrogen protons are forced into inner spiral chains. They cannot move in 3 dimensions. They can only flow along well-defined helical or spiral pathways embedded within the carbon structure. Ronald Cohen noted in a press release that the atomic motion is not fully 3-dimensional. Instead, hydrogen moves preferentially along well-defined helical pathways.
An analogy can help illustrate this. If superionic water is like a crowded room where people, the hydrogen, are freely milling about between stationary pillars of oxygen in all directions,
Then this new carbon hydride phase is like a spiral staircase. The people, the hydrogen, are still moving, but they are strictly confined to walking up or down the spiral tracks dictated by the architecture, which is the carbon. The matter isn't just flowing, it is being channeled like microscopic wires in a planetary scale circuit board.
that's a very vivid image. This immediately suggests how this kind of directed flow could influence a magnetic field.
Which is exactly the connection that paper makes to solve the planetary mystery. But before getting there, it's important to understand how this state was discovered, because lasers or diamond anvils were not used for this.
That's a critical point for listeners. Magnetic fields are known to be skewed because Voyager 2 physically measured them. Superionic water is known to exist because it was created in a lab. However, humanity currently lacks the physical laboratory equipment to sustain 3,000 gigapascals and 6,000 Kelvin while simultaneously taking an atomic snapshot of carbon hydride.
Drilling into Neptune is not possible. So the question is, how do Liu and Cohen know this quasi-1D spiral structure exists? Their methodology relies on first principles, or ab initio, quantum physics simulations using high-performance supercomputers.
First principles calculations. That sounds very fundamental.
It is. It is considered the gold standard of theoretical physics. These calculations do not rely on empirical assumptions, historical data fitting, or best guesses. Instead, they start directly from the fundamental laws of quantum mechanics, like the Schrödinger equation and density functional theory. The researchers input the basic quantum properties of carbon and hydrogen atoms, apply the mathematical parameters of extreme pressure and temperature, and then let the laws of physics dictate how those atoms must behave.
So essentially, pure physics equations are used to predict atomic behavior under conditions that cannot be replicated on Earth.
Exactly. Historically, simulating the quantum interactions of hundreds of atoms over time was incredibly computationally expensive, even for the most powerful supercomputers. But Liu and Cohen integrated advanced machine learning algorithms to accelerate these fundamental quantum simulations. The machine learning models learn the quantum mechanical forces between atoms from smaller, rigorous datasets, and then scale those rules up to simulate large, complex atomic frameworks over longer timescales.
So it's not just a guess or hypothesis. It's a rigorous mathematical prediction based on fundamental laws enhanced by cutting-edge computational power.
That's the crucial point. It's vital to communicate that while this is a simulation, it represents a rigorous mathematical prediction. In the realm of high-pressure physics, computational models frequently precede physical discovery. For instance, ice-18, the superionic water discussed, was predicted by computer simulations long before the 2019 laser experiment successfully verified its structure. Liu and Cohen's 2026 prediction of quasi-1D superionic carbon hydride now serves as a target for the next generation of experimental physicists. For now, supercomputers are the most rigorous and often only laboratory for testing matter at these extremes.
This returns to the core mystery. How does this spiraling hydrogen, predicted by these supercomputer simulations, explain a magnetic field tilted by 59 degrees and offset by a third of the planet's radius?
Magnetic fields are generated by the movement of electrical charges, the dynamo effect. If the mantles of Uranus and Neptune were made of a standard isotropic fluid where charged particles move equally in all directions, the resulting magnetic field should be relatively uniform, or at least not so dramatically skewed.
But the paper shows the electrical charge isn't moving uniformly.
Correct. The paper demonstrates that in the deep mantle, the electrical charge carried by those mobile hydrogen protons is highly restricted. Because the protons can only move along quasi-one-dimensional helical pathways inside the carbon lattice, the electrical conductivity of the material becomes highly anisotropic.
Anisotropic, meaning it conducts electricity exceptionally well in specific directions and poorly in others.
Precisely. If a massive planetary layer exists where electrical currents are forced to flow in restricted directional spirals, the resulting dynamo will naturally be asymmetrical, constrained, and off-center. The geometry of the superionic lattice at the atomic level scales up to dictate the geometry of the magnetic field at the planetary level.
So the microscopic helical flow of hydrogen creates a macroscopic, lopsided dynamo. That's a compelling mechanism.
It offers a compelling mechanism to date for why the magnetic fields of the ice giants are so lopsided and stable. It transforms the chaotic soup into a highly structured electrically directional material.
And this isn't just about Uranus and Neptune, is it? Thousands of exoplanets have been discovered, many of them mini-Neptunes.
That's the broader implication. As Kong Lu stated in the paper's release, carbon and hydrogen are two of the most abundant elements in the universe. If this quasi-one-dimensional superionic state of carbon hydride exists in Uranus and Neptune, it's highly probable it's one of the most common materials in the universe, existing in the interiors of countless other ice giants and many Neptunes across the cosmos.
So this isn't just solving a 40-year-old mystery in the solar system. It's potentially revealing a fundamental state of matter that dictates the physics of planets everywhere.
It certainly is. The insights from this work could reshape understanding of exoplanetary magnetic fields, and by extension, their potential for habitability or atmospheric retention. A planet's magnetic field is a powerful shield, and understanding its generation is crucial.
It's remarkable how a problem that seems so specific to two planets in the solar system ends up having such universal implications. This paper delivers profound insights.
It highlights how solving one puzzle often reveals connections to a much larger picture. The detailed structure of matter at extreme conditions inside a planet can directly explain its observable large-scale properties.
So, the key insights here are that the bizarre magnetic fields of Uranus and Neptune, an anomaly for decades, can be explained by a new state of matter, quasi-one-dimensional superionic carbon hydride. This material, found under extreme pressure and temperature, forces hydrogen protons to flow along specific helical pathways. And this directed anisotropic flow of charge creates the lopsided tilted dynamos observed by Voyager 2.
And importantly, this exotic state of matter, predicted through advanced quantum simulations and machine learning, is likely not unique to the solar system. Given the abundance of carbon and hydrogen, it's probably one of the most common materials in the universe, shaping the fundamental properties of a vast number of exoplanets.
That changes the way one thinks about what's inside a planet. Instead of a simple liquid core or mantle, it's a dynamic, structured environment where matter behaves in truly unexpected ways.
Indeed, it forces a reevaluation of what is considered solid or liquid under planetary conditions.
This prompts the question, what other forms of matter, currently beyond experimental reach, might be shaping the worlds beyond view? That wraps up this episode of Paper Trail. Join us next time as we dig into more research worth talking about. If you liked what you heard, share it with a friend.
Keep reading the fine print.